This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So today we're going to look at problem set 4, and in problem set 4 what we're trying to do is design a feedback control system that is part of a gravity-fed water distribution network, and the role of the feedback control system is to regulate the water level at the downstream end of each so-called pool along an irrigation channel. And that's an important operational objective because in order your capacity to supply flow further downstream or to end users via supply points at the end of these pools under the power of gravity is determined by the water level. Okay, if you like, the water level is the amount of potential energy stored available to push water further downstream or onto farms at the supply points. Okay, so just to give you a little bit more context, I'll show you a video. Okay, so this is work that's that we've done here in collaboration with an industry partner called Rubicon Water. Okay, and this is a little bit about a project to modernise the irrigation networks in northern Victoria.
Smart water technology is revolutionising the operation and management of open canal irrigation water distribution systems around the world, reducing the massive amounts of water lost in transit from storage to farms. Using the world's limited water resources efficiently is becoming increasingly important as the world faces scarcity in many regions. With 70% of the world's fresh water used for irrigation, authorities are looking to reduce water lost in inefficient irrigation infrastructure. In Australia and around the world, canal automation is being implemented to reduce these losses and secure more water for productive uses. In one of the leading projects of its type, the Northern Victoria Irrigation Renewal Project, or NVIRP, is underway in Australia's Murray-Darling Basin. It will secure the future productivity of Victoria's food bowl irrigated agricultural region, while delivering major environmental benefits. The project is automating Goulburn Murray Irrigation District's 6,000 kilometres of canals, and together with targeted remediation and rationalisation, it will see over 425 gigalitres of water saved each year, a figure similar to the amount of water consumed by the City of Melbourne's 3 million inhabitants. Previously, the district was losing massive amounts of water through leakage and seepage, inaccurate metering, and poor control that results from manual operation. It is now being transformed into a modern and efficient supply system that makes the best use of precious water resources. The project's technology is the result of many years of research and development undertaken in conjunction with the University of Melbourne. Called Total Channel Control, it is the world's first fully automated end-to-end canal automation system, enabling efficient operation that is on par with pipe networks, but without the associated costs. It achieves these outstanding results using a combination of precision water control gates, known as flume gates, accurate system-wide flow measurement, wireless radio networks, automated meter outlets, and sophisticated software. The project is transforming the district on a large scale, with some 10,000 flume gates being installed across thousands of kilometres of canals. The entire network is centrally managed using software which automates every aspect of the operation: customer ordering, planning and scheduling, automatically controlling the farmer's outlet, and customer usage and entitlement reporting. Networks of flume gates precisely measure and control the flow of water, constantly adjusting to ensure optimal system operation. Human intervention is only required to address any problems that are identified by comprehensive diagnostics. And through accurate measurement, the system is able to identify high-loss sections of canal for targeted remediation, ensuring limited maintenance resources can be spent to achieve maximum benefit. The technology is achieving outstanding results, with some large-scale operations achieving up to 90% efficiency. The Goulburn Murray Irrigation District is already seeing improvements of around 20% in parts of the district that have been automated. The resulting water savings are being made available for urban uses, returned to river systems, and used for further irrigation. Additionally, Enverb is delivering major service improvements for irrigators. Water can be supplied within 2 hours of ordering and at high and constant flow rates, enabling farmers to achieve major efficiency improvements on farm.
Yeah, on my farm, what it's allowing me to do is to grow a lot more tonnes per megalitre because we're getting bigger flows, consistent flows. The consistency is probably the big thing, you know, to go for a couple of hours and then slow up. Now it's exactly the same rate for the exact amount of time, so you can plan it a lot more efficiently. Straight away I can go onto the computer, pretty much water it on demand.
With a modernised supply system, farmers are now able to take efficiency to the next level by automating their on-farm irrigation operation, maximising crop yield and quality while reducing water use. And all this is achieved by harnessing gravity to move water and by using solar-powered gates, meters and radio networks. The Enverb project is a true low-energy, low-carbon solution.
Okay, so let me just show you another little short video to explain roughly how it works, and then I'll provide some more detail.
Rubicon's Total Channel Control automatically manages every aspect of canal operation to precisely measure and control the supply of irrigation water. By using a combination of feedback and feed-forward control, Total Channel Control minimizes fluctuations in canal water levels, ensuring a consistent supply to all farms. Customers also benefit from near on-demand service and the flexibility of ordering their water online or over the phone. When an order is made, software automatically checks if the customer has sufficient allocation and whether the order can be delivered within capacity constraints. The order is then sent to the customer's turnout. It automatically opens at the requested time and continually adjusts to deliver the ordered flow rate. Upstream flume gates anticipate the downstream demand using feed-forward control. And along with real-time level and flow information, continuously adjust to maintain water levels immediately downstream. As each regulator adjusts to maintain the water level in its downstream pool, upstream regulators in turn adjust right through to the reservoir. This means that only the exact amount of water required is drawn from the reservoir, eliminating the spills and wastage that plague traditional irrigation infrastructure. Total Channel Control, changing the way the world irrigates.
Okay. So, as I mentioned at the beginning, the technology that you've just heard about is the outcome of a long-standing partnership between the University of Melbourne and Rubicon Water. It has positioned Rubicon Water as a world leader. So Rubicon now sells this technology all around the world, in the US, in Europe, in China, and they've just secured a $250 million contract in India to automate the large irrigation networks, close to the border with Pakistan. Okay, so what we're going to look at in problem set 4 is how we went about designing the lowest level controllers. Okay, and these are basically feedback controllers that regulate the water levels at the downstream end of each pool to reference levels that are determined on the basis of demand, and it corresponds to regulating the capacity to supply flow under the power of gravity, if you like. The water level is how much potential energy is there to push the water downstream or onto a farm. Okay, so it's an important operational objective is to keep that level regulated, not wobbling about too much, okay, which makes the jobs of the supply point gates easy in terms of the adjustments they have to make to deliver specified flow. Okay, so all right, let me just try to provide some more detail. So the system that we're talking about is a water distribution network. Okay, so there'll be some source. Okay, and that source might be a lake or a reservoir, or it might actually be a river. Okay, and then there's a network of open water channels. Okay, so a side view of a channel, so looking on the side there, a side view might look like this. You have some bottom slope. Whoops, what am I doing? Some bottom slope, okay, very gradual, okay, and along these open channels there are these regulating structures, okay, that can be adjusted, okay, and those regulating structures are usually positioned just downstream of supply points to so-called secondary channels, all right, and they will also be located along the channels situated just downstream of supply points to end users. In other words, farmers. Okay, so there will be these regulating structures all along these channels. Okay, and the job of the control system is to make adjustments to the positions of those regulating structures in order to maintain the water levels just upstream of those structures at set points that are consistent with the expected flow demand. All right. Okay. So the flow of water throughout the network is entirely powered by gravity. Okay. So flow is in this direction. Okay. Flows from upstream to downstream. Okay, and by adjusting the position of these regulating structures, you gain some authority over the flow downstream. Okay. Now, traditionally, these systems were operated manually. There was a human being that used to go up and down the channel, and it was as simple as pulling drop bars out of the channels, okay, or putting them in to regulate the flow. So the opportunity for taking control action was very limited. It maybe happened once a day. All right, and so in order to deliver, the required quality of service to the end users, there was a tendency to oversupply. Okay, so release more from here than was actually required, just to make sure that the water levels were sufficiently high to allow gravity-powered supply to the end users. All right, and as a consequence, what happened is that you ended up with a lot of outflow at the bottom. Okay, and typically in these networks, there's no real opportunity for recovering water that flows out of the bottom of the network. Okay, in some cases, there's another river down the bottom and it just goes back into that. But in many cases, there's no opportunity to recover any excess flow that's released from the source. Okay, and so apart from wasting water, all right, it causes all sorts of problems, including bringing salt to the surface, which then ruins the land and you can't use it for growing crops anymore for another 10 years. All sorts of problems. All right. So the control system in place at the lowest level, and there's actually a hierarchy of control, but we're just going to look at the control system at the lowest level, results in demand-driven release of water from the source. Okay? And it works like this. So we've got an irrigation channel. It's an open water channel of the kind that you saw in the video. Along the channel, there are these regulating structures, okay, that can be adjusted. All right. And the way they're adjusted is under the action of feedback control. And that feedback controller is, so we've got flow down like this, okay, by adjusting the position of the gate relative to the upstream water level, you can set the flow. Okay. So the way the control system works is we measure the water level. Okay, so you take a measurement of the water level, it gets compared to a reference. Okay, that reference needs to be set. It's set by a part of the control system higher up in the control hierarchy on the basis of demand. Okay. If you like, that set point reflects your capacity to supply flow further downstream under the power of gravity or onto a farm. And the controller looks at the error and makes an adjustment to the flow over the upstream gate. All right? So what happens when there's increased load downstream, all right, or a farmer starts to draw water from the channel, what happens is that the water level drops. Okay, it's just a bucket, if you like, and I start taking water out of it, more than's coming in, so the water level drops. And so you get a reference error, you get an error, okay, and the controller takes action by increasing the flow. Right? And if that's done properly in steady state, what happens is that the flow at the commanded by the controller for the upstream gate will reach a steady state value that matches the flow load. Okay? So that's the job of the controller. It's trying to adjust this to match the load flow. Okay, if this system reaches equilibrium, if the water level returns to the set point and stays there, it's telling you the net flow must be zero, right? And so the action of the controller ends up matching the flow over the upstream gate to the load flow. All right. Now, of course, the action of the controller here is a disturbance on the upstream pool. Okay, by increasing the flow here, that will cause a water level error in this pool, okay, and the controller for that pool will take corrective action by adjusting the flow over its upstream gate. All right, and it's in this way that a change in the flow load down here propagates upstream all the way to the source, resulting in demand-driven release of water from the lake or river upstream. Okay, so it's these decentralised controllers acting together, responding to each other's actions in a way that propagates towards the source that results in demand-driven release of water. And because we're having demand-driven release of water, you're never releasing more than is actually required, and so we can actually achieve zero outflow at the bottom. And that's where the big efficiency gains come from the perspective of water distribution efficiency. Okay, so what we're going to focus on is how to design just one of these controllers for a pool. All right. What makes this a challenging problem is the interaction between the controllers, but we're not going to worry about that today. Okay. Okay. Are there any questions on this so far? Is it clear what the control objective is and why we're doing it? Yeah, no questions? Yeah.
What if one of the dam gets damaged, and would the load be compensated by the next controller?
You can put things in place to handle things like that, but we're not going to discuss that today, right? It's yeah. Any questions? No? All right, so to do control system design, we need some sort of model. Okay, so we're just going to look at one pool. Okay, so a pool is a stretch of channel between regulating structures. What we're trying to do here is control the water level at the downstream end. Okay, that's where we will be supplying flow to farmers, and that's what farmers want. They want flow. They don't just want, a volume over any period of time. They want flow. Often these are, flood irrigators, right? And so they need a specified flow at the supply point to make sure that the water reaches the end of the paddock. Okay. So there's flow onto the farm and there's flow downstream. We're measuring the water level, comparing it to reference, and controlling the flow over the upstream gate. All right. So we've got the water level here. Let's call it Y. Okay. And let's call this flow downstream V. Let's call this flow D, and let's call this flow U. All right. Now, the relationship between all of these variables is, can be described very simply, right? Not exactly, but a good description of the relationship between these variables can be derived on the basis of effectively conservation of mass, right? So this is, if you like, just a bucket of water, all right? So the volume here, assuming that the cross-section of the pool is roughly constant along the channel, will be, some constant. It'll equal some constant times the water level. All right? And we know that the rate of change of volume, okay, which will just be C times Y dot, will be equal to the net flow. All right? And the net flow is just the difference between U and V plus D, right? V and D are going out and U's going in. All right? But these channels are very long. The distance between this regulating structure and this regulating structure, could range anywhere from a few hundred metres to a few kilometres. Okay? So the impact of adjusting the flow here on the water level downstream is delayed. Okay? What happens, you make an adjustment here and then a wave propagates down the channel, okay, and it takes time for the wave to propagate down the channel. So, we need to take that into account when determining the net flow under this very gross approximation that the volume is roughly a constant times the water level. Okay, so we make the net flow such that the rate of change of volume at time t, or the rate of change of the water level down here, will be equal to a delayed version of the flow here, all right? and the current load. All right, so that's our model for the system. This is our control input. This is a disturbance input. And really what our control system is trying to do is reject changes in the disturbance, right, from the perspective of maintaining the water level at some reference value. Okay, so that's where this model is coming from. Okay, yeah, I called it C. Here it's just alpha, right? Same thing. It's just a constant, right, which relates to the cross-sectional area of the, the surface area of the channel. All right. This is your control input, which is delayed, and this is your load. Yep.
Why gravity is not a function of light?
Why is gravity not a function of these? Well, it does arrive in the partial differential. It does arise in the partial differential equations that really describe the relationships between these variables. But this is an approximate model, right, that we're just going to use for control system design, and it's based on conservation of mass. Right, gravity is a force, right, and it will relate to conservation of momentum, and we're not accounting for that in this simplistic model. Right, but a model is something that we're just going to use to design guide control system design. And really, the reason we can get away with the simplistic model is because we only care about the water level at the supply points at the downstream end. We don't really care about what the water level's doing further upstream. Okay, if you want to know what the water level's doing further upstream, then you have to account for gravity. And effectively what happens is that further upstream, in order for water to flow under the power of gravity, right, in order to have flow, you need you need a wedge like that, right? So that this has higher potential energy than down here, and that causes the flow. Okay, so gravity will affect the profile of this little wedge, but all we're caring about is how to control the water level down here. All right, if you want to know, the profile of this wedge that leads to flow along the channel, then you need to account for what you're talking about. Make sense? All right, but we're only trying to regulate this. We're not trying to regulate the water level all the way down. So we don't need a model that describes the spatial distribution of the water level along the channel. To do that, you need a much more sophisticated model. Okay, but this model matches very well the actual behaviour of this water level when you're changing the flow out and the flow in. Remarkably well. And in fact, the way we build these models is by doing system identification experiments, right? Either by simulating these partial differential equation models that are non-linear hyperbolic PDEs, right, that account for conservation of mass and momentum, and then we fit parameter values that I'm not showing here, just to keep them in the model simple. In the full models, there's parameters in front of these things as well. Okay, and you get remarkably good match between the behaviour of this model and real data. Okay, but it relates. We get away with it because we only care about the water level down here. We don't care about how it's distributed spatially along the channel. Okay. All right, where was I? Okay. So, problem set 4 is really about trying to, figure out how to design the control system. So there's a bunch of questions here, right? And, it's trying to get you to go through the steps that one might take to design a control system. So we've started with the model, all right? Now we might want to draw some sort of block diagram description of the closed loop system, all right? And then the rest of the questions here are really about, looking at different types of controllers, starting from a proportional controller to a controller that is effectively a PI controller, right? So we'll just go through those, right, just so that you can see the steps that one might take to design a control system. All right. So let's start with the block diagram. All right, we've got this model that's saying alpha times the rate of change of the water level is, equal to the difference between a delayed version of the flow upstream and the load. All right, so if I take that into the Laplace domain, what am I going to get? I'm going to get alpha s y s equals e to the minus s tau u s minus, well, let's just call this L, right? And denote its Laplace transform with the corresponding capital letter, right, as we've done for the other signals. All right, so this says that y of s, the thing that we're trying to control, is related to the control input and the disturbance via a transfer function that looks like 1 on s, or alpha s, right? E to the minus s tau u of s minus L of s. Okay? And what our controller does is it measures the water level and feeds that back to be compared to a reference to generate an error signal that is processed by the controller, which sets u. All right? So this is the block diagram, and you can see that it's consistent with this equation, right? So, the other equations here is that, us will be the controller transfer function times the difference between the reference and a measurement of the water level. All right, so the block diagram is just a graphical description of this equation and this equation. Right? So this is just forming what's in here, right, as the sum of L, an input disturbance, right, and a delayed version of the control signal. All right, here's the integrator that then converts that signal into a water level. All right, this is describing the construction of this signal here, the difference between the reference and the water level, okay, and U is just the action of the controller on that error signal. All right, so that's how we get the block diagram, and you can see that the external inputs consist of a reference for the water level and a load disturbance. Okay, so the objective of the control system is to keep the water level at the reference despite changing load. Right, so it's really a load disturbance rejection problem. Okay, when this changes, it'll have an impact on the water level, but the controller takes corrective action to bring the water level back to the reference. All right, so, all right. Now, what was the second question? The second question was about saying, well, let's consider a controller that's just equal to 1. And it's saying, well, generate a Nyquist plot of the corresponding open loop transfer function. What's the open loop transfer function? Well, if C, the open loop transfer function is just this. It's what you get when you break the loop, right? So it's the product of all of these things is the open loop transfer function. And we're saying what happens when C is equal to 1? Well, when C is equal to 1, you get this as a Nyquist plot. All right. So our open loop transfer function, lambda s, is equal to C of s times G of s. Our C of s is 1. Our G of s is e to the minus s tau on s. Okay. And if you look at this at low frequency, so really the Nyquist plot is just a polar plot of lambda j omega. All right. And for small frequencies, you would expect lambda to have infinite magnitude, right? Because we've got the s on the bottom, right? So if we evaluate that at s equals j omega and set omega equal to 0, the magnitude of this will be infinite, right? What would you expect the phase to be? Well, the phase of this is the phase of, so the phase of lambda j omega will be minus omega tau, right? Minus pi on 2, right? Because you've got the s there, right, on the denominator. So at omega equals 0, right, we just get a phase of minus pi on 2. So for low frequencies, we would expect the Nyquist plot to have large magnitude and phase of minus pi on 2. So we're down here for small frequencies. All right? And as we increase frequency, it moves around. And what's happening here is that things are whizzing around 0 because of the delay, which we've seen before, right? So as we continue to increase frequency, this phase keeps on getting more and more and more negative. So it causes it to spin around like that. All right? And then, as we go, so the Nyquist D contour that we have to go around in this case, because we've got a pole at the origin, looks like this. So we've looked at what happens when we start at a small frequency, go up here. As we go around here, the magnitude will be 0, right? As we let the radius here go to infinity. And so you get stuck at 0 inside here. And you come around here, and as we pop out, you just get the mirror image of what we had before, right? So it pops out, and then it comes up like this, all right? Which takes us to here, all right? So if this is epsilon, and that's minus epsilon, we're saying this is omega equal to epsilon, this is omega equal to minus epsilon up here, right? Remember that each point in the Nyquist plot just corresponds to a different frequency, right? So we've identified as this frequency being down here. As we go around here, we're at 0, and this frequency corresponds to minus epsilon. As we go around here, we know we get half a revolution in the clockwise direction, a net change in phase of minus pi radians, right? Which is giving us this around like this, right? Corresponding to moving s around here, a little indentation around the pole at s equals 0. All right? Now, for closed loop stability, we want no encirclements of the critical point -1. Okay, the critical point -1 is somewhere over here. That's minus 0.4. So that's somewhere over here. All right, so we're not getting any encirclements of the critical point, which is what we want for closed loop stability, because the number of open loop right half plane poles is 0. Right? So for stability, we want no encirclements of the critical point, and that's what we're getting with C equal to 1. All right? What this is showing is that when C is equal to -1, all right, what happens to the Nyquist plot is that we're effectively multiplying this guy by -1. What does multiplying something by -1 do? It shifts it, it rotates it in phase, right, by the phase of -1, which is pi. Okay, so what's happening is this it rotates, everything rotates around, the axes of the complex plane. This is the imaginary axis and this is the real axis. All right, so it just rotates around like this. So the imaginary axis is here, okay, and you can see that what's happened is that this point has been rotated around to the other side. Right? There it is there. Okay, and in this case, with C equal to -1, you see that the half revolution in the clockwise direction that you get when you're going around the little indentation around S equals 0 now causes an encirclement of the critical point -1. Remember, this is happening at infinite magnitude, right? So it's definitely going to be on the other side of -1 when it crosses the real axis. Okay? So you will get a clockwise encirclement of the critical point, right? So n will be equal to 1, but p is equal to 0. All right? So you can't, having the controller be -1 will lead to an unstable closed loop, right? Whereas having the controller C equal to +1 will lead to a stable closed loop. Right, so this is just an exercise, if you like, to show you how to use Nyquist plots. Right, that's all I'm trying to explain here. So, but it suggests that you can stabilise the system with just a proportional gain controller. Right, if closed loop stability is the only thing you care about. Of course, we care about more than just closed loop stability. But from the perspective of closed loop stability, you can stabilise this system with just a constant gain controller. All right, but you can't have arbitrarily large gain, right? Because if we increase the gain, if we now make the controller equal to k and we start increasing k, what's going to happen to the Nyquist plot? Remember, scaling just expands or shrinks the Nyquist plot. Doesn't rotate it, right? Because we're, let's say we've already figured out that we need a positive gain. Right? So it's not going to rotate it, it's just going to expand or shrink it. And if we expand by increasing k beyond 1, this point here will start moving this way. Right? And if we make k sufficiently large, this point will move to the other side of the critical point. All right? And if it moves to the other side of the critical point will be like inside here. And as we're following this around, coming out the other side, we will end up with encirclements of the critical point when we don't want any. All right? How many encirclements will you get? You'll get 1, 2. All right? And although this looks like it's whizzing around all on 0, it's whizzing around, and sometimes it's intersecting the negative axis again and again and again. Right. So the first time this crosses over to the left of -1, you end up with 1, 2 unstable closed loop poles. But if you keep on increasing k, what happens is that you end up with even more clockwise encirclements and even more unstable poles in the right half plane. Now, you might be wondering, well, how's this possible when I've only got one open loop pole? Well, it's possible because of this irrational part of the transfer function. All right? So you've got to be careful of that. Right? But the point is that there's a limit on how big the gain can be. Well, why might we want to push up the gain? We might want to push up the gain to reduce the amount of steady state error that we have when there are changes in the load. Right? If you go and work out, what the steady state error is and how it depends, for the load. So if we go back to the block diagram, we can get 0 steady state error here for step changes here, right? Because of that integrator there. But if we have step changes here, we won't get 0 steady state error in response to the step changes here. As we saw last time, in order to get perfect rejection of step changes at the in the plant input disturbance, we needed, by the internal model principle, for disturbance rejection, an integrator in our controller. Having one in the plant wasn't enough. All right? Now we're trying to reject changes in the load here, right, which will be more or less step changes. As the farmer turns on their demand, it's like a step change in the flow load, right? And that can't be rejected perfectly in steady state unless we have an integrator in the controller. But we can reduce the amount of error by increasing the gain of the loop. Just do the analysis, right? I think maybe it's already in here. Right, so there might be there's motivation for increasing the gain of k, but because of the delay, we have to be careful. We can't increase it too much because if we increase it too much, we end up with an unstable closed loop. Okay? All right. How big can we make the gain before we lose closed loop stability? Well, it's a question of when will this cross the -1 point, right? So if for c equals 1, this point here is 0.2, I can increase the gain by a factor of 5, and if I make it by a factor of 5, that'll just be sitting on the critical point and we'll be on the boundary of instability, or it would be just unstable. Okay, so we can have a gain of up to 5, but we can't go beyond 5. Right, and that can all just be read off the Nyquist plot. Okay. All right, so what else is there? So that's 3. Question 4 is about constant gain controller K, which is what we're looking at. Determine the sensitivity transfer function. Well, that's just algebra, right? So let's just look at the algebra. You know, it's asking for the sensitivity transfer function that relates the input disturbance to the error. Okay, and so you can, it's just algebra from the block diagram. It looks like this. Okay, and if the system is stable and we put a step change in the disturbance, the error will reach a constant value, right? And so you can apply the final value theorem, right, to figure out what the steady state error is. Okay, there's nothing stopping you from applying the final value theorem just because this is an irrational transfer function. Right? And it's an irrational transfer function because of the delay. Okay, so this stuff here is just about working out, well, if I put a step change in the load, L, right, and this is the Laplace transform of a 0.1 metre cube per minute step change in the load. This is the transfer function from the load signal to the error signal. This is what you get. Because this is a stable transfer function, provided k is less than 5, right, then it'll reach a steady state value. We can then apply the final value theorem to work out what that steady state value is by looking at the limit as s goes to 0 of s times the Laplace transform of E. And so if you do that in here, right, so you've got s times this, right, so this s here kills that s there, and then we take s to be 0, all right, and so this just becomes 1 on k, right, and then we're just left with 1 on k times this 0.1. So this shows you that increasing k is going to reduce the steady state error for a step change in the load. So that's our motivation for increasing k. But as we've seen, we can't make it we can't make k too big, right? Because if we make k too big, the system will be unstable. And if the system is unstable, we can't do this analysis, right? In order for this to make sense, we need to know that the closed loop is stable. Right? So before applying the final value theorem to do this sort of analysis, make sure that the transfer function involved is stable so that you know that a step change at the input will result in a steady state constant value, right? Because that's the assumption that underlies the final value theorem. All right. Okay, so number 6. It's asking about how big the gain can be to make sure that the closed loop sensitivity transfer function has a peak gain of less than 14 dB, right? So this is about how close the Nyquist plot will get to the critical point. As we've seen before, the closer you are to the critical point -1 with your Nyquist plot, the more peaking you get in the sensitivity function. We saw a relationship, right? In fact, one measure of how close your Nyquist plot, the measure corresponding to drawing little circles around here until you hit the Nyquist plot is telling you about the peak gain, right, in the sensitivity function, right, because the little vector from -1 to the Nyquist plot is 1 plus lambda, Right, so 1 divided by the smallest this can be will give you the peak gain in the sensitivity function, which is 1 on 1 plus lambda. We've seen that before. Right, so to answer this question, it's really about going and looking at the Nyquist plot for different values of k, right? And as we increase k, as we've seen before, so this is k equal to 1, right? Increasing k just expands the Nyquist plot, right? And so you can see it expanding, right? This is k equal to 2, this is k equal to 3, this is k equal to 4, right? The Nyquist plot is just expanding out. As it's expanding out, what we can see is that the Nyquist plot is getting closer and closer to the critical point -1. And so as we're increasing k, you would expect to get a bigger peak, maximum peak in the sensitivity function. All right? And so this question is saying, well, make sure that the sensitivity peak is less than 5, right? So I've got to draw a circle of radius 0.2, 1 on 5, right? Because the little vector from -1 to any point on the Nyquist plot is, the vector 1 plus lambda, and s is 1 on 1 plus lambda. So if I want s to be less than 5, I want 1 plus lambda to be bigger than 0.2, right? And you can see when k is equal to 4, we're not satisfying that for the range of frequencies corresponding to this part of the Nyquist plot, right? So you can't have gain 4, but you can have gain 3, right? Because when the gain is 3, then the Nyquist plot is always further away from the critical point than 0.2. So the sensitivity peak will always be less than 5. Okay, so this is just showing you how to use the sorts of tools that we've been learning about to assess a feedback control system and to inform design decisions about how big a controller parameter can be. Okay, while worrying about, for example, how much peaking we get in the sensitivity function. Okay, so you can see that in these plots. Okay, so this is showing the output sensitivity function, 1 on 1 plus lambda. Right, at low frequencies, this is small. Why? Because at low frequencies, lambda is large because we've got an integrator in lambda. And so at s equals 0, that's got infinite magnitude. So that's why it's low down here. All right. Increasing k is pushing the gain down. Right? So it's making the output signal, the error signal less sensitive to changes in the external inputs. Okay? But what's happening is we end up with more peaking in the sensitivity function. And that will typically give rise to more oscillations in the step responses of the closed loop system. Because remember, a step input doesn't just have energy at 0 frequency, it has energy distributed across a range of low frequencies. In fact, it has energy at all frequencies. You get this sync function. All right, so a step change is going to have some energy at this frequency. And the peaking up here suggests that, well, that component of the step change will be amplified, and that's what causes the oscillations in the transient response. I think there are some, there they are there. Right? So you can see that, when the gain is large, making you have this peak in the sensitivity function, you get this more oscillatory response compared to when the gain is low and you get this transient response that doesn't have any oscillations. All right? We're running out of time, so we'll pick up from here on Monday and then start looking at part 4 of the notes. All right, so have a look at the rest of problem set 4. There's not much to go, all right, so that we can quickly finish it off on Monday.
The border plot, why there are wiggles and when
Because of the delay. It's an irrational transfer function. It's not rational anymore. It's because of the delay.
and the delay is getting affected and not at lower frequency, it is only getting affected at higher.
It's most significant at high frequency. We'll see. The next example is about saying, let's pretend there's no delay there. And now design a PI controller, assuming that the plant is really just an integrator, no delay, right? And then we'll say, well, but there is delay. So what's, are we robust to the presence of delay? And so we look at the modelling error, and you'll see it becomes more significant at high frequency than at low frequency. So you're right, the delay is more significant at high frequency than the impact of the delay is more significant at high frequency than low frequency. Make sense? Thanks.